In January 2019, something unusual happened in the quiet world of geophysics. The U.S. National Oceanic and Atmospheric Administration and the British Geological Survey issued an emergency update to the World Magnetic Model a full year ahead of schedule. This model, which underpins everything from smartphone compasses to military navigation systems, was drifting so far from reality that it could no longer wait for its routine 5-year refresh. The magnetic North Pole was moving faster than our models could track it. Scientists at the National Centers for Environmental Information scrambled to recalculate the position of a pole that had, in just 2 decades, sprinted across more than 200 kilometers of Arctic territory. This was not a minor adjustment. It was an acknowledgement that something fundamental about our planet's magnetic behavior had changed, and we were racing to keep up with it. What makes this particularly striking is that for most of human history, the magnetic poles were reliable. They wandered, certainly, but predictably. Sailors could trust their compasses. Cartographers could map magnetic declination with confidence that their charts would remain accurate for decades. That era of stability is over. The magnetic North Pole, which spent centuries meandering through the Canadian Arctic, is now charging toward Siberia at speeds that have stunned researchers. In this video, we will explain how scientists discovered this acceleration, what it reveals about the planet beneath our feet, and why tracking these changes matters more than ever in our technology-dependent world. Let's get started. The story of tracking Earth's magnetic field is relatively recent in human terms. While ancient Chinese navigators used lodestone compasses as early as the 11th century, systematic scientific measurement of the magnetic poles only began in earnest during the 16th century. Early explorers noticed that magnetic north did not align with true north and that this misalignment varied by location. This difference, called magnetic declination, became crucial for accurate navigation. By the 1830s, scientists like Carl Friedrich Gauss were developing mathematical frameworks to describe Earth's magnetic field as a global phenomenon rather than a collection of local measurements. The breakthrough came with satellite technology. In 1999, Denmark launched the Ørsted satellite, followed by Germany's CHAMP mission in 2000 and the European Space Agency's Swarm constellation in 2013. These satellites carry instruments called magnetometers that measure the strength and direction of the magnetic field from orbit. Unlike ground-based measurements, which are affected by local magnetic materials and electrical systems, satellites provide a clean global view. They circle the planet continuously, building up detailed maps of how the field changes across space and time. This is how we discovered that the magnetic field is not static. It is a living, breathing aspect of our planet that fluctuates on timescales from seconds to millennia. The World Magnetic Model exists because modern technology demands precision. GPS provides location, but many systems still rely on magnetic heading for orientation. Aircraft autopilots, military targeting systems, directional drilling for oil, and even the compass app on your phone all depend on accurate magnetic field data. The model is essentially a mathematical representation of Earth's magnetic field that allows any device anywhere on the planet to calculate the local magnetic vector. It is updated every 5 years under normal circumstances. The fact that researchers pushed through an emergency update in 2019 tells you everything you need to know about how rapidly the situation was evolving. The reason for that emergency update becomes clear when you look at the data. Historically, the magnetic North Pole moved about 10 to 15 kilometers per year. This was manageable. Navigation systems could be updated on schedule. But around 1990, something changed. The pole began accelerating. By the year 2000, it was moving at 50 kilometers per year. That is roughly 137 meters per day. This is not a gradual shift, it is a sprint. The pole has now traveled from its traditional location in the Canadian Arctic, crossed into international waters, and is heading directly towards Siberia. If you plotted its path on a map, you would see a trajectory that has become increasingly linear and directed over the past 3 decades. Scientists measure this movement using a network of magnetic observatories scattered across the high latitudes, combined with data from the Swarm satellites. The satellites orbit at about 450 kilometers altitude, passing over the poles roughly every 90 minutes. Their magnetometers detect variations in field strength down to fractions of a nanotesla, which is about 1/50,000th of Earth's total field strength. This precision allows researchers to track not just where the pole is, but how the underlying magnetic structure is shifting. What they have found is that the pole's movement is not random. It is driven by changes in the flow of molten iron deep in Earth's outer core. The outer core is a shell of liquid metal about 2,200 kilometers thick, sitting beneath the solid mantle. Temperatures there exceed 4,000 degrees Celsius, and the iron is in constant motion, driven by heat escaping from the even hotter solid inner core. This flow of electrically conductive fluid generates electric currents, which in turn create Earth's magnetic field. This process is called the geodynamo. The field we measure at the surface is the combined result of countless swirling currents and eddies in that hidden ocean of metal. When those flow patterns change, the magnetic field changes with them. Recent research has identified specific structures in the core that explain the pole's acceleration. Using mathematical models that work backward from satellite data, scientists have mapped regions of concentrated magnetic flux at high latitudes. Think of these as invisible mountains and valleys in the magnetic landscape. There is one flux lobe centered beneath Canada and another beneath Siberia. For most of recorded history, the Canadian lobe was stronger, anchoring the magnetic pole in North America. But observations show that the Canadian lobe has been weakening and stretching, while the Siberian lobe has remained robust. This imbalance is pulling the pole eastward like a game of magnetic tug-of-war. The discovery of a jet-like flow of molten iron beneath these regions, moving at speeds of up to 40 kilometers per year within the core, provides a mechanism for this shift. The fluid motion is literally dragging the magnetic field lines along with it. While the pole races north, another magnetic phenomenon has scientists equally concerned. The South Atlantic anomaly is a region where Earth's magnetic field is significantly weaker than anywhere else on the planet. The field strength there has dropped to less than 30,000 nanoteslas compared to a global average of about 50,000 nanoteslas. This weakness has consequences. Earth's magnetic field normally deflects charged particles from space, trapping them in bands called the Van Allen radiation belts. These belts orbit safely above most satellites, but over the South Atlantic, the weak field allows the inner radiation belt to sag downward, bringing high-energy protons and electrons closer to Earth's surface. This creates a hazard zone for satellites. Any spacecraft passing through the anomaly is bombarded with radiation levels far higher than normal. The Hubble Space Telescope, which orbits at about 540 kilometers altitude, passes through this region regularly. Mission controllers have programmed it to shut down its sensitive instruments whenever it enters the anomaly to prevent radiation damage. The International Space Station, orbiting at 400 kilometers, also passes through the region, requiring extra shielding to protect astronauts from elevated radiation exposure. Commercial satellite operators report increased bit flips and computer resets when their spacecraft traverse this zone. A bit flip occurs when a high-energy particle strikes a computer chip and changes a 1 to a 0, or vice versa. For critical systems, this can cause malfunctions or even total failure. What makes the South Atlantic anomaly particularly intriguing is that it is expanding. Measurements from the swarm satellites show that the region has grown westward over the past 2 decades and has decreased in minimum field strength. More surprisingly, recent data suggests the anomaly may be splitting into 2 separate centers of weakness. This bifurcation indicates that the magnetic structure beneath South America is becoming more complex. Researchers believe the anomaly is caused by a patch of reverse polarity magnetic flux in the outer core beneath the region. Essentially, the iron down there is generating a field that points the opposite direction to the main global field. Where these opposing fields meet, they cancel each other out, creating the weak spot we observe at the surface. The connection between the racing pole and the growing anomaly lies in the overall behavior of the magnetic field. Satellite measurements confirm that Earth's dipole field strength has decreased by approximately 9% over the past 2 centuries. A dipole field is the simple bar magnet-like field with one north pole and one south pole. This is the dominant component of Earth's magnetic field, but it is not the only component. The field also has more complex multipolar structures. As the dipole weakens, these non-dipolar features become relatively more prominent, leading to effects like the South Atlantic anomaly. The weakening is not uniform. Some regions lose strength faster than others, creating the patchwork of strong and weak zones we observe today. Understanding these changes requires looking beyond the surface measurements to the engine that drives them. The geodynamo is a self-sustaining system powered by the planet's internal heat. As the inner core slowly crystallizes, it releases latent heat and lighter elements that rise through the liquid outer core. This compositional convection, combined with thermal convection from residual heat left over from Earth's formation, keeps the outer core in constant turbulent motion. The rotation of the Earth adds another twist. Literally, the Coriolis effect causes rising and sinking columns of iron to spiral, creating the complex helical flows that generate the magnetic field. This is not a smooth, steady process. The core is in a state of turbulent chaos, with jets, eddies, and waves constantly forming and dissipating. What scientists have learned is that the geodynamo does not operate in a steady state. It goes through phases of relative stability and phases of rapid change. We appear to be in one of the rapid change phases. Computer simulations of core dynamics suggest that changes in the temperature difference between the inner and outer core, or in the heat flow at the core mantle boundary, can trigger shifts in the flow patterns. These shifts propagate through the core over decades to centuries, eventually manifesting as changes in the surface magnetic field. The timescales involved are vastly different from anything humans experience directly. A major change in core flow takes thousands of years to fully play out, but we can detect the beginnings of these changes with our modern instruments. The geological record provides context for what we are observing. When lava cools, magnetic minerals within it align with Earth's magnetic field, creating a permanent record of the field's direction and intensity at that moment. By studying volcanic rocks of different ages, scientists have reconstructed the history of the magnetic field going back millions of years. This record shows that the field has reversed its polarity hundreds of times. During a reversal, north and south poles swap positions. The most recent reversal, called the Brunhes-Matuyama reversal, occurred about 780,000 years ago. The intervals between reversals are irregular, ranging from tens of thousands to millions of years. The fact that we are currently in a long period of stable polarity has led some researchers to suggest we may be overdue for the next reversal. The changes we are seeing today, the accelerating pole and the weakening field, are consistent with the early stages of a reversal, but they are also consistent with a geomagnetic excursion. An excursion is like an aborted reversal. The field weakens and the poles may wander toward the equator, but then the system stabilizes and the poles return to their original configuration. The Lachamp event, which occurred about 41,000 years ago, was one such excursion. The field strength dropped to about 25% of normal for roughly 500 years before recovering. Determining whether we are heading toward a full reversal or just experiencing a temporary fluctuation requires more time and data. The process of a reversal takes thousands of years. We have high-resolution satellite data for only about 25 years. We are essentially trying to predict the outcome of a slow geological process by observing its first few moments. Understanding these changes has consequences beyond pure science. Our modern infrastructure is deeply intertwined with the magnetic field. Aviation is the most immediate concern. While GPS provides position, many aircraft systems still use magnetic heading as a reference. The World Magnetic Model Update in 2019 was necessary specifically to keep these systems accurate. As the pole continues to move, these updates will need to happen more frequently. Airports have already begun renumbering runways. Runway designations are based on their magnetic heading, rounded to the nearest 10 degrees. Runway 27, for example, points at 270 degrees magnetic. As the field shifts, the heading changes, and the runway must be redesignated. This is not just a matter of painting new numbers. It requires updating charts, procedures, and pilot training materials worldwide. The weakening of the magnetic field poses a different kind of challenge. Earth's magnetic field acts as a shield against the solar wind, a continuous stream of charged particles from the sun. When a solar storm erupts, sending a burst of high-energy particles toward Earth, the magnetic field deflects most of them toward the poles, where they create auroras. A weaker field means less deflection and more particles penetrating into the atmosphere. These particles can induce electric currents in long conductors like power transmission lines. During the 1989 Quebec blackout, a geomagnetic storm caused transformers to overheat and fail, plunging millions of people into darkness for 9 hours. As the field continues to weaken, our vulnerability to such events increases. Satellites face the most direct threat. The expanding South Atlantic anomaly means that more spacecraft will spend more time in higher radiation environments. Current satellite designs include some radiation hardening, but they are calibrated for the historical field strength. If the anomaly continues to grow and split, satellite operators will need to either increase shielding, which adds weight and cost, or accept shorter operational lifetimes and higher failure rates. For the massive satellite constellations being deployed for global internet coverage, this could translate into billions of dollars in additional costs or lost revenue. Looking forward, the scientific community is expanding its monitoring capabilities. The European Space Agency is planning follow-on missions to the Swarm constellation to maintain continuous coverage. NASA and other agencies are developing new magnetometer technologies with higher precision. Ground-based observatories are being upgraded with better instruments and faster data transmission. The goal is to build a comprehensive real-time picture of the magnetic field's evolution. This will allow researchers to refine their models of core dynamics and improve predictions of future changes. There is also growing interest in drilling deeper into the Earth's crust to study magnetic anomalies more directly and in developing better computer simulations that can model the complex fluid dynamics of the outer core. In practical terms, industries that depend on magnetic data are adapting. The aviation sector is accelerating the transition to satellite-based navigation systems that do not rely on magnetic heading. Oil and gas companies that use magnetic surveys for exploration are investing in more frequent calibration and validation of their instruments. The military, which uses magnetic anomaly detection for submarine hunting, is developing new algorithms that account for the changing background field. These are incremental adjustments, not crisis responses, but they reflect a growing recognition that the magnetic environment is no longer static. The story of Earth's wandering pole is ultimately a story about scientific discovery in real time. For the first time in human history, we have the tools to watch our planet's deep interior in action. The acceleration of the magnetic North Pole, the expansion of the South Atlantic anomaly, and the gradual weakening of the field are all windows into the behavior of the geodynamo 3,000 kilometers beneath our feet. These are not disasters, they are data, they are evidence of a dynamic, evolving planet that is constantly rewriting its own magnetic signature. The emergency update to the World Magnetic Model in 2019 was not a warning of catastrophe, it was a testament to our ability to detect, measure, and respond to planetary change with precision and speed that would have been unimaginable just a generation ago. Right now, satellites are circling overhead, measuring magnetic field vectors with exquisite accuracy. Ground stations are processing that data, feeding it into models that simulate the flow of iron in Earth's core. Navigation systems are being updated to reflect the pole's latest position. Within the next decade, as computational power increases and more satellites come online, we will have an even clearer picture of how the geodynamo operates and where the field is heading. Within our lifetimes, we may witness the magnetic North Pole complete its journey across the Arctic and settle into a new configuration, or we may see the field begin to stabilize and strengthen again. This is not just a geological curiosity, it is a living demonstration that the planet we inhabit is far more active, far more complex, and far more fascinating than the solid ground beneath our feet suggests. And we are watching it unfold in real time.